All right, so we have our first polynomial, 5x squared plus 20 plus x cubed plus 4x. What's the first thing wrong with it that we've worked on in the past weeks? Not in descending order, so let's put it in descending order. What is the highest exponent in the list? Good, x equals 3. Thank you, Bryce. So that means we have approximately 3 solutions. 3 solutions. I'm sorry, what did you say? Now, yesterday we talked about when you get imaginary solutions, but we didn't do any of them. So today, if you graph this on your graphing calculator, the 0 you would see would be -5. If we did synthetic division as we did in yesterday's homework, you would find out that -5 is a 0. Therefore, how would it be a factor? Instead of letting this be 0, let's let it be x plus 5. Why? Why did I change the 0 to a factor? Do what? Because when it hits the x-axis, that is actually a 0, but to actually go back to the polynomial, you have to make it a factor. Now, we are at x squared plus 0x plus 4. Now, how do I know I start with x squared? Because I started with x cubed and divided by x, which leaves me an x squared to begin my depressed polynomial. By depressed, it doesn't mean sad. By depressed, it means lower exponent. Now, I know that this is an imaginary solution. I don't know if you know it's an imaginary solution. So we are going to resort to the quadratic formula. Because if we're going to find the solutions, we have to be able to simplify a trinomial by the quadratic formula down to its solutions. What's the problem with the square root of -16? So it would be plus or minus 4i over 2, which would simplify to be plus or minus 2i. So now we have 2 imaginary solutions. How do we change them into factors? So if you have x equals 2i, you subtract it from both sides. That says x minus 2i equals 0. That's factor 1. Then you have x equals negative 2i. Add 2i to both sides, and x plus 2i equals 0. So when you have an imaginary solution, you also have to know how to turn it from a 0 or a solution into a factor. So then in my list up here, I need x minus 2i and x plus 2i. And if I multiply all that out, it goes back to my polynomial in decreasing order, or my messed up polynomial, either one, without being in decreasing order. How did I get x minus 2i and x plus 2i? The quadratic formula gave me plus or minus 2i as a solution. I have to go from a solution to a factor. There is a small shortcut I'm going to show you right here. Wouldn't this be x squared plus 4 equals 0? So therefore, couldn't you say x squared equals -4, square root both sides, and it would be plus or minus 2i. Couldn't you get to the solution just a little bit faster than the quadratic on that one? What did you say, Isaac? Quite a lot faster. You still have to change the solution to a factor, so then you would end up with x plus 2i, x minus 2i. Example 1, taking what we learned yesterday and moving from just being in the real solutions to the imaginaries. The question says how many zeros at most could you have? What is it? Sorry. 4 zeros. And because it said the word zeros in the problem, that implies that there's no imaginary solution. So if you graph this guy, -1 is the first hit you see on the x-axis. Why do I need a 0? Go ahead, Haley. It's got to be a placeholder because we don't have an x. Perfect. Do your synthetic division. And is -1 indeed a factor? If it is, how do you know? Anybody know? Yes or no? Is -1 a 0 that we can turn into a factor? Ooh, I heard yes, lots of yeses. How do you know? Good, because the 0 remainder. Perfect. Now, let's look at the graph. Are there any others that seem like they might be a 0? We've checked -1, it worked. What do you think? Looks like 3 is going to be 1, okay? Now, this is our first exposure to a cubic having more than one root. Remember when we did parabolas at the beginning of the year? And a parabola would come up, touch the x-axis maybe at 3, and we'd call it a double root or a double solution because at 3 right there, it comes, it doesn't cross, it's tangent and goes down. Well, look what is happening here at 3. It is touching. At first it doesn't cross its tangent, but then it ends up crossing. So let's see what special thing happens. Let's use our 3. We just keep going in synthetic division. Is 3 a solution? So let's do one little bit of finesse right here. The solutions are x equals -1 and x equals 3. How do you turn them both into factors? Good. This is what we were talking about, Michaela, right here. To make sure when you get a 0 that works, that you change the sign when you make it a factor. There's nothing in common with 1, -6, or 9. So if I potentially might have a double root, I'm going to check 3 again. And what happened? It worked. So I have another 3. Well, I'm supposed to have 4 zeros. Let's check 3 again. And sure enough, x equals 3 is another solution. What do you call it when the same number is the solution 3 times? Triple root. Nothing more complicated or fancy than that. We don't have to worry about changing fractions in our factors because all of our leading coefficients were 1. See, there was a 1 in each one of those positions. But we can write our polynomial in factored form now. And you could write it x minus 3 cubed if you wanted to. So these are our solutions, all listed down the side, and then I wrote them as products of factors. if you can go forward like this and you can pull your solutions out, then you have to be able to take solutions or x-intercepts and create the polynomial going backwards. So that's what we're going to do next. A quick example 2, not very fancy. Example 3. You have the leading coefficient of 1. You have the zeros, -1, 2, and 4. And I want you to create a polynomial knowing that the leading coefficient is 1 and those are the zeros. What is the first thing you do with the zeros? Turn them into what? Good, Cassie. Sammy, good. So those zeros are now changed to what? Factors. Now, on the last test, some of you missed the product of 3 binomials still. So, somebody tell me how they would attack this. Let's go to Derek. How would you attack 3 multiplication problems of binomials? Okay, you'd start with the first 2, that's fine. And he said the FOIL method. All right, so first times first is x squared, outside times outside, -2, inside times inside is 1x, and -2. Anything there I can put together from the FOIL method. Okay. Now I have my 2 products of 2 binomials. Now I have a trinomial times a binomial. How would you do this one, Megan? Now that you have a trinomial times a binomial, what would you do? No idea? Do you want to phone a friend? We can't call it FOIL because it's not a binomial times a binomial, but you can use the properties of FOIL and distribute, okay? So, to keep it straight, draw your little lines. X squared times x gives us x cubed. X times -4 is -4x. So I have now distributed just the x squared. Next, I would do -x times x is -x squared, and -x times -4 is what? What's wrong?
What if the -4x squared?
Where, sweetie?
After
X
x cubed.
cubed -4. Yes, you get a point for that. Good job. All right, now the last thing we need to do is we need to distribute the -2. So -2 times x is -2x. -2 times -4 is +8. What do I do to wrap this up? Help me, Sydney. Wrap this up at the end. Combine like terms, perfect math language. So those go together. These 2 make -5x squared. These make +2x, and that makes +8. That's going backwards from zeros to the polynomial. The reason it worked is because our leading coefficient was 1. Did we end up with a leading coefficient of 1? Yes. Did you want me to answer something for you? Okay. What if my solutions I gave you were a little trickier? You have the solutions of x equals 4, x equals 2 plus 3i, x equals 2 minus 3i, and a leading coefficient of 1. So you have 1 real, 2 imaginary solutions, and a leading coefficient of 1. First thing you have to switch is from solutions to what? Factors. What would you make the first one, Danielle? Perfect. What would you make the next one, Riley? Remember, you have to move everything to the other side. Close. When you move the 3i from plus to minus, what would you do? -2 minus 3i. On the next one, Derek, what would you do? There you go. Now, what's the problem with this big, nasty looking problem? What's the problem with this problem? It's a bunch of junk, isn't there? If you have two imaginary numbers that are conjugates, why do we remember these are conjugates from earlier in the year? The imaginary part is what, Will? What? Right, they're the same but different. The signs are changed. Okay, so if you have two conjugates, then I would start with the box method and I would multiply the conjugates first. Trinomial x negative 2 negative 3i times x negative 2 positive 3i. Once you create your box for the box method, it's much quicker to see if things are going to cancel or what you're going to have to do. On any of those, Bryce, where they made the decimal and not the fraction on those papers, I just counted it wrong. Do you see anything that will cancel with negative 3xi, Haley? Good. So those will make a zero pair. Any other zero pairs, Nathan?
6i and 8.
Perfect. So we've got x squared. We can put these two together as negative 4x plus 4 minus 9. But I squared, we always changed into what? Negative 1. So we really have x squared minus 4x plus 4 plus 9 times 1 is 9, and negative times a negative is a positive. So we have in the final step of just the trinomial times the trinomial, x squared minus 4x plus 13. Am I done with the problem? No, and that's the pain in the butt of it. It's so huge. Trinomial times trinomial gave you a trinomial that then you have to multiply by the binomial you haven't used yet. Again, I'm partial to the box method, so I would use the box method on x negative 4 times x squared minus 4x and 13. And again, several people missed this on the test. It was a binomial times a trinomial from earlier in the year, also from Algebra 1. Worries me just a little bit. Did y'all get negative 52 on that? So we have x cubed. These two do not cancel, so we've got negative 16x squared. That looks like a positive 13x and a positive 16x, so that is 29x minus 52. So when you combine like terms from the box method, you get binomial times trinomial to be a 4-term polynomial. You could call it a cubic. You could call it a 4-term polynomial. This is going backwards, given that you also had partial imaginary solutions. Next, I'm going to teach you something very old school. Questions over there? Yes, Riley. Because negative 4 times negative 4x is 16x. I multiplied negative 4 times negative 4 to get 16.
Yeah, but I mean the negative 4x squared plus the negative 4x squared.
I don't have a negative 4x squared plus.
Oh, yeah, I see what she's saying. That's minus 8.
Oh, yes, Riley, you get a point for that. Do you see where she's talking? I'm sorry, I was in the wrong box, Riley. Negative 4 and negative 4 add up to be what? Good. So you do get a bonus point. Sorry, Riley, I was in the wrong box. She is correct. Descartes' rules of signs is old-fashioned. Do you remember when you guys asked me, I don't know if it was first period or sixth period yesterday, and you said, how do you, when you have so many P over Q fractions, how do you know where to start when you don't have a graphing calculator?
Yeah, here's Nikki.
Was it Nikki? Okay. Well, Descartes' rule of signs is how I did it when I was in high school and even in college. Ooh, trying to get bonus points.
I can't do it anymore. Apparently it's like a one-time thing.
Brownie points. Bonus brownie points.
I just don't like this.
Now, first, we are going to check for how many real positive solutions there could possibly be. No, Isaac, total solutions could be 6, but not real positive solutions. Did you all hear what Isaac said? He immediately said 6. Now, 6 is the possible of all the solutions you could get. So he's right there, but we're just going to check for real positives first. You're looking for sign changes. Is this positive? Did it change to negative? That's one sign change. Is this negative going to positive? Another sign change. Is this positive going to negative? Another sign change. Does it change any more to the end? So you could have real positive solutions of 3 or 1. Does anybody know why I can't have 2?
That would go back at the same time.
It has to do with imaginaries, hint, hint.
Because the square root of -2 next to the 5th is measurement.
Does anybody know how imaginary numbers travel?
How they travel.
How do they travel?
They do like completely opposite direction of everything else.
When they are solutions, they travel in pairs. So if you have 3 real solutions, you're fine. But if you only have 1 real solution, how many imaginary solutions can you have? 2. You can't have 1. Okay? Because they have to be in pairs.
Yeah, I see where you're going.
Now let's do real and the negative possible solutions. F of negative x. Does anybody know what happens when you sub in a negative x for a positive x and the x? Stop, Isaac. You're just wasting time. It doesn't turn upside down. Negative x subbed into x, if it is an even power, what does it do when you do negative times negative times negative times negative times negative times negative? What is always going to happen to all those negatives? They all cancel to be positive. But what if I cancel my negative, or I substitute my negative x into a odd power? I end up with negative times a negative is a what? Positive 2x to the 5th. So then it stays the same because x to the 4th is positive, or is even. But what's going to happen when I put this negative in for x cubed? Be negative 10 times negative x cubed, which you're right, would be positive 10x cubed, Tristan. Now, what's going to happen when I put the negative in for the even exponent of 2? Stays the same. It's going to change that guy to plus 8x. Does it do anything to the constant negative 8? No. And you assume that to be a 1, so it's odd. Now, to find the possible or potential real negative solutions, was there a sign change? No, no, no. What happened here? Sign change 1, what's happened here? Sign change 2, what happened here? Sign change 3. So you could have 3 real negatives or 1 real negative. How many total did Isaac say we had maximum at the beginning? 6. So we could have 3 and 3, right? That adds to 6. I could have 1 and 3. Uh-oh. That's only 4. I could have 1 and 1. That's only 2. How many do I have total? So what are we going to fill those leftovers with? We have to fill it with imaginary. Good. Okay, now our total we already know is 6. You have to have 6 solutions because the power of 6 is the highest power in the polynomial. Let's look at real solutions that are positive. I could have 3 of them. What could I partner that with that are real negative? What are my choices down here? Okay, so I'm going to fill it with 3. How many imaginaries do I have then? They have to add across the 6, so we have none. What if I go back and have 3 real ones again? What is the other choice I could have for real negative solutions? How many do I have total if I have 3 reals that are positive, 1 real that's negative? 4, right? So how many imaginaries do I have to fill in there? Because they have to add up to what across there, Jessica, when I'm done? Perfect. So 3 plus 1 is 4, plus 2 is 6. I have now used up my positive real 3. What do I have to check next, Shelby? Got to check the 1. So I'm going to fill the 1 in. What could he be paired with? 3 negatives. How many total is that? Kinsey, what do I have to have here to add up to 6?
2.
Have to have 2. Good. Now I'm going to go back to the 1. I haven't exhausted all my choices yet. This time, Perla, what am I going to match the 1 with in the negatives? I don't have 2 as a choice. I only have 3 or 1, and I've used 3. What's left? 1. That gave me 2. I know it's crazy. So, Sammy, what's going to go here? How many imaginaries do I need to get a 6? 4. So you have 2 pairs of imaginaries. Don't y'all think that's fun? What's the matter with you?
I'm human. That's why I don't
Nikki would be loving this. All right, why don't you guys have to spend a lot of time on Descartes' rule?
We were born in 1891.
And neither was I, but thank you for that age.
Well, I'm not going to get into brownie points here, so. It's a lot of fun.
All right. I'm asking you for the solution. Would you go to Descartes' rule to try to see which P over Q's you would like to use? Say no. You would graph it, and what would you see on the x-axis? A hit where? At -2. Good. Good job, DeMarcus. Why do I have 2 zeros there? Placeholders. Good.
Okay, screensaver.
Oh. What am I left with? 1x squared minus 2x plus 4. You graph that thing, and it's not going to hit the x-axis. So you know you have 1 negative real. And what solutions do you have down here? 2 imaginary. How are you going to find them? When you see me write A, B, and C, you know what's coming. What is it? Quadratic. How do I know that's imaginary, guys? Do I know it's imaginary? How? Square root of any negative is imaginary. Now, what is this going to break into? Square root of -1 is I. Square root of 4 is 2. Can you do anything with the square root of 3? Will it reduce any further from that factor tree? Let's write it out the long way first, just in case you don't remember. Square root of 4 is 2. Square root of -1 is I. Square root of 3 over 2. But my 2 is over both terms, correct? Final answer. What is my imaginary solution? 1 plus or minus. What happens to the 2 over 2 right here? Cancels to be 1. So I have 2 imaginary solutions. one negative real solution. Did the technology make this a whole much better? Yeah, because did you have to do this whole thing and then check all the P's over Q's? No. Like, we didn't even finish this problem over here. We haven't even found a 0 yet. What have we found? Options that it could be out of. What was the biggest amount of solutions you had in P over Q last night? Was it 9 opposite pairs? Was it that? Did I give you any that big? Number 3, what did it have in it? 6 opposite pairs. So 6 had 7. So the most you had was 14 opposite pairs. So in 14 opposite pairs, could you have done a whole lot of work still, even with this chart? Are you happy about technology? Yeah, absolutely. All right, let's write down the homework. Bless you. Bless you. Now you're going to write the question, show your work, circle your answer. Number 42 asks you to give a 0, and it is irrational. So let me remind you quickly what you do. Did everybody get that written down? 20 through 24 even. I'm going to talk about 42, but I'm going to show you with x cubed plus 8. Now remember, we already saw that it hit at -2, but I want to prove it. So you zoom 6 it, you let it hit again, and we are looking for the hit on the x-axis. What thing on there represents, what word, a solution? 0. So pick number 2. It says, are you left of the 0? I am not. I'm up on the y-axis, so I have to hit my left arrow key till I'm left of it. Enter. Am I right of it? No. So I have to hit the right arrow key till I'm what? Right of that -2. And what does it tell me the 0 is? Was I right? So when you do number 42, I'm telling you it's irrational. You're going to get an ugly decimal for the answer for 42. Questions? Everybody got the assignment written down? Everybody got the notes written down?